I would like to introduce now the last speaker of this first session today, Dorina Thanou. She's a lecturer and senior researcher here at EPFL and works on the application of machine learning models and AI for robust and interpretable AI and has a specialization in signal processing.
Thank you so much for the introduction. Hello, everyone. It's a great pleasure to be here, actually, after a long break from this COVID situation. So thanks a lot, the organizers, for making this happen. So today, I will talk about robust and interpretable learning methods for healthcare. Basically, the topic is quite broad, but I will try to highlight some of the aspects that I'm more interested in my research, but I also believe that these could be key aspects in the adoption of these methods in clinical applications. So basically, one of the reasons why we are all here today is because, as was mentioned in the previous talks, we have much more data than before. So due to these great technological advancements, we might have imaging technologies that are much more advanced, that they can capture information at a level that we could not believe that it would be feasible a long time ago. So nowadays we can have information at the cellular level, we can go deeper into the molecule, into the genome, etc., and also, and also at the same time, this might be combined with different clinical information. This might be a very, very rich set of data from which we could extract intelligence and provide support to people working in clinical aspects or in medical research. So, of course, this generates a lot of opportunities for machine learning, since we are in a machine learning conference, but the answer to the question of how can we apply machine learning to this type of data is not that easy. So a basic naive approach could be that we take this data, we feed them to a machine learning model, we train a lot of parameters, which might be the case, for example, of classical deep learning architectures, the problem there, and we try from these models to get some actionable knowledge. The problem there is that that might not be so easy just because of the medical data setup. So typically, what we do in other applications is we have some data, let's call it X. We try to design a model, F, in a machine learning language that takes X as an input, learn the parameters of this model, and then get some actionable knowledge that could be diagnosis, prediction, etc., etc. Now, why that is not so straightforward for machine learning applications? First of all, it's because of the data quality. In many healthcare applications, we, fortunately, most of the time have to deal with unbalanced data sets, which means, for example, we might have patients that from a tumor type that is very rare, or we might have patients that had myocardial infarction, but the number is very small. So that might generate a lot of trouble for machine learning algorithms due to the fact that you have this kind of imbalance between healthy and unhealthy patients, or between different rare type of disease, in order to have a set of training data sets that could be meaningful to learn robust models. A second point is related to the complexity in this data. So usually, as it was mentioned in one of the previous talks, so in many applications, in many healthcare applications or in many healthcare data sets, these data have an underlying structure. Think, for example, of a gene network, a protein-protein interaction network, or even a biological knowledge graph that was discussed before. So there is an underlying structure there that if we want to really exploit the power of this data, we need to take into account that structure. And last but not least, another important issue is the adoption of these algorithms in practical settings. And the one very key question there is the interpretability of these models. So we will never be able to apply these methods, again, in clinical settings or in decision-making in healthcare if we are not able to have some understanding of how these methods work, why these methods can assist in the decision making in this type of applications. And nowadays, the current machine learning literature, it's considered to be what we call black box, in the sense that we tend to go into models that are more and more huge in terms of learning parameters, as we call them, but at the same time, we tend to understand them less. So there is a lot of research in the direction of trying to understand these machine learning models in order to get more interpretability and foster the adoption of machine learning in medical applications. So robustness, structured, and interpretable learning, I think these are three keywords that are needed in order to develop the new generation of machine learning algorithms that can be useful in healthcare and health in general. So if we want to think of AI or machine learning, if you want to make it a bit more precise for healthcare, what we need to think is a new way of designing these algorithms that would be driven by the three points that we mentioned before. And how can we achieve that? One way of doing that is by trying to integrate as much priors as we have in machine learning language. We call that inductive bias. In a simpler language, we can say that whatever knowledge we know from the data, the expertise that we have from the clinicians, the expertise that we might have from industry in the domain or from scientists working in similar applications, we should try to find a way to inject this knowledge into our learning system. And at the same time, as I mentioned before, there are many data sets where you have some structure already. So introducing that structure into the model might lead to the design of algorithms that are more robust and much more efficient in medical applications. So for the rest of the talk, I will focus on one specific aspect, that is, how can we exploit structure in the data? And in particular, in many healthcare applications, we have data sets that are represented by complex networks. Think, for example, of a brain. You have different regions of a brain connected with the synapses. We are interested in understanding the biological organization of the brain, and networks seems to be there in terms of the understanding. Also, protein-protein interaction network is another network that is very well known in the literature, but also knowledge graphs, as were mentioned before. It's a different type of network where you have nodes combining different modalities, comorbidity networks that are networks of disease, but also if you think of medicine at the system level, we might have networks at the gene level, at the protein level, going at the cell level, but then at an organ level and also at the patient level. So this is just to motivate the use of graphs that, again, they were mentioned before as flexible structures to capture some of the complexities of the data that might exist in medical applications. So some of the typical machine learning tasks we're dealing with this type of data in healthcare. First of all, it's about predictive tasks. So one of the questions that we usually ask ourselves is a patient going to survive or not? Or is the patient going to express a disease in the future, in a few months or a few years from now? And for example, if you take the case of a tissue in oncology, then you might be able to capture the cells, and you would like to understand from the interaction of the different type of cells if the person is going to respond to a therapy or not. On the other hand, there is also the reverse task of trying to understand new knowledge that is about knowledge discovery. So the question there is more, can we find predictive biomarkers? How can we reveal new knowledge that we don't know before that might be an indicator if a person, for example, is going to have a good or a bad prognosis? Or, for example, in the case of the brain, how can we understand what is the underlying biological mechanism? So these type of tasks are not really predictive, but they go more into the direction of discovering new knowledge from the data. So how can we design graph-based machine learning for healthcare by taking into account some structure in the data? So here is a very general high-level slide of what could be in one slide, if I can say, the literature in graph machine learning today. Basically, you go from a setup, before we had as an input data X, now you have as an input data, but also some prior that is given by the graph. So the input of your model in this case is the data and the structure in the data itself, which is a graph. And of course, the output, what you want to predict in a predictive task, it depends on the application. It could be a prognosis, it could be a clustering task, it could be any output that could be relevant for the application. But the key difference is that now, instead of taking into account only the data, you take into account the structure of the data or the domain of the data. And of course, there is a lot of literature and ongoing research. It's quite a hot topic nowadays on how can you define this type of models, starting from a signal processing perspective, so trying to define what are good transforms, but defined on data that live on networks, on graphs, and what I mean by transform, you might probably have heard about Fourier, wavelets, all these kind of feature extraction methods, basically, that can be used to extract knowledge from the data, from a signal processing viewpoint, but also from a pure, more ML, if you want, viewpoint by generalizing notions such as convolutional neural networks or deep learning in general in graph settings. So these are all, it's an active area of research and methods coming there every day and I believe that it's an area that is going to be very promising for the next couple of years as well. So this type of tools is, if designed properly and if designed with an application mindset in mind, with the constraint coming from the application, can be quite useful in terms of predictive tasks when you have structured data as an input. So the second task that I mentioned before, it's more about knowledge discovery. So what I mean by there, if we want just a simple formulation, is that now we don't necessarily have the structure given. We have an assumption that there is some structure of the data, but we would like to infer that structure. If we take just the example of the brain, we would like, for example, to understand what is the structural functional organization of the brain for different states. So, for example, when we are in a resting state or when we are performing specific tasks. So graph-based machine learning could be also used into this type of applications where basically by introducing some assumptions that you might have in the data coming from the domain, you are able to reveal some complex interactions in the case of the graph. So you can think of it as the inverse task, basically, of the prediction one that we had before. Before we had the graph as an input, and we would like to predict something, a task, basically a predictive task. Here we would like to predict complex interactions. That would reveal some new knowledge that we don't know about the data. So, let me mention briefly a few applications where this type of tools can be useful. First of all, the first one is about autism spectrum disorder. So in this work, we have tried to understand if combining the structural organization of the brain together with fMRI signals can be helpful in order to predict if a person is an ASD or a neurotypical subject. Basically, the idea is that if you combine both sources of information, you are able to extract more meaningful patterns that would be better for prognosis. So the type of tools that we use there are inspired from the graph signal processing literature. So we try to extract features in the frequency domain by trying basically to understand how the fMRI signal is changing on the brain and over time. And these features are given as an input to I will skip the details, I guess, but these discriminative features are given as an input to a simple classifier that is a decision tree that can also help in terms of interpretability. So both building blocks, projecting the data in a subspace that is interpretable through the Fourier representation on the graph, but also the use of simple classifiers could lead to an algorithm that you can understand what could be the nice features that could be predictive for this specific task. So in terms of results, you can see here just briefly in the y-axis the accuracy, the higher the better. In the y-axis, the size of the training set, how many data we have in order to learn these models. With blue, we see the performance that we get when we combine both the structural information but also the information of the fMRI signal. And the other two curves are if we take into account only the structural information and or the information of the with the red curve, the information of the fMRI signals without taking into account the brain structure. So we see a significant gain if we combine the information from both type of sources and by extracting these discriminative features. And as I said before, the nice thing with the framework is that you can get really interpretable features. I'm not an expert, I should say, in the domain of neuroscience, but after discussing with people working in the area, we realized that some of them discriminative features for patients in autism spectrum disorder are indeed activated in the areas of the frontotemporal areas that are known to be related to ASD patients. And for neurotypical patients, the features are more activated in parieto-occipital areas. The second application that I would like to mention, for which I'm really excited about because I believe that it's a domain where this graph-based techniques can have a lot of impact, it's in cancer research, here in particular in digital pathology, sorry. So this is work that is done by some of our colleagues here at EPFL, and it's basically trying to use graphs in order to capture dependencies between cells at a cell level, but also at a tissue organization level. So using graph-based machine learning tools such as GNNs and hierarchical GNNs give you much better results than trying to blindly feed these images into a machine learning pipeline. So by taking into account the knowledge that you might have that the spatial organization of the cells is important, but also the organization in terms of hierarchies of the tissues is also important, you can get an accuracy and a performance that is much better in terms of prediction. In the collaboration, in ongoing collaboration that we have with the oncology department here in CHUV, we are trying to see how we can use these type of tools, graph-based machine learning tools, in order to find biomarkers for immunotherapy. The idea there is that there is an underlying assumption, and there is a lot of works saying that the spatial interaction between immune cells and different type of immune cells and cancer cells is quite important. And that's one of the hypotheses that we are trying to explore in that direction with our clinical collaborators. What we are trying to do there is exactly bridge this bridge between pure ML models, but also clinical knowledge by verifying hypotheses that are coming from the clinical domain. For example, if you consider these images, they contain billions of cells. So if you go at a cell level and if you analyze all of them, of course, it's quite tough because the number of images that you will have will be very limited because the number of patients that you will have will not be very high. So it might really make sense to focus on regions of interest, of areas where, from the medical point of view, you have a hypothesis that might be quite interesting and quite useful. And that's exactly what we are trying to do in this type of collaboration. We have some first preliminary results that shows that indeed by focusing in this particular case in the area between tumor and between cancer and stroma, and extracting graph-based features in that domain could be quite important in terms of prediction. The next application that I would like to mention is in the domain of oncology. Again, this is another collaboration that we have with our partners, clinical collaborations at CHUV, where we are trying to predict myocardial infarction for future events, for patients coming in the hospital with some mild symptoms, basically. And coronary angiograms, invasive coronary angiograms, are the standard procedure and the standard imaging techniques that interventional cardiologists are using in order to decide if a person should be treated or not. So the goal of this specific project is to see from these images we are able to predict if a person is going to have an event in a couple of years from now. So initially, the study that we did was purely at an image level, but again, guided from the clinicians. So the clinicians were the one indicating the regions of interest where they see a stenosis, and also to what extent this stenosis should be significant. And then, on the top of that, we were applying a deep learning algorithm on the images in order to be able to predict if this type of techniques could be used for myocardial infarction. It's a very small clinical study, so it's 80 patients. So in terms of machine learning and data and deep learning, it's quite small. So by no means we can claim that these are results that can be extended, but we are trying to see if this type of results in a bigger clinical study right now can be generalized and can be promising. But from this small clinical study, it seems that deep learning indeed can have, guided by the knowledge of the physicians, of the clinicians, can have some performance that could be quite significant. And the question is, can we do better than that? And the answer is hopefully yes, and that's what we're trying to do again in the same setup now by not taking only into account the images, but taking into account the geometry of the vessels. So you can reconstruct the geometry of the vessels from these images, which can be represented as a mesh or a network or a graph if you want. And we can use this geometry together with features from the images, but also knowledge that you might have from hemodynamics. There is a lot of research trying to see how, for example, features like the wall shear stress, designed from simulations, but from some knowledge that we know how, what is the flow, for example, and the pressure on the arteries, can be useful in this type of applications. So this is, again, a very interesting and collaborative project in the domain of how can we use graph-based machine learning tools enhanced with knowledge from the domain, from the clinical domain, for healthcare applications and in cardiology specific, in particular. The last application that I wanted to mention, it's related more on the task of knowledge discovery that I mentioned before. So the previous ones were more predictive tasks. So here, this one is a knowledge discovery task. It's done from, again, some of our colleagues here at EPFL. It's a very recent work. The idea is that you try using graph-based signal processing and machine learning tools to understand different organizations of the brain over time. Basically, you see here the results about two different tasks, language task, emotion task, and you see that these results basically are, in the first state, what you recover is the resting state of the brain, which is supposed to be consistent across different tasks, at least in terms of activation patterns, but then you recover different states that, for example, in the emotion are related to the fear, that is quite different from what you get in the neutral task, where you have the visual cortex that is mainly activated. So this type of findings show that you can indeed extract information about the dynamics and the different organization of the state of the brain that could hopefully be useful for understanding some pathologies in brain applications. So what is next? So I discussed about structured and interpretable learning, and I mentioned a few points, I highlighted a few key ideas, but there is much, much more work to do. And I think that work comes from a direct communication with clinical partners, with the application domain in general, in order to define AI methods for medicine that could assist doctors in taking decisions, that could assist, that could help enhance their existing knowledge with some data-driven tools. But at the same time, we can use AI, we can use biology, which is a very complex ecosystem, as a very promising playground for developing new AI tools and new machine learning tools. So by taking these applications into account, we might reach at some point the design of novel methods that could go into the direction of being more generalizable and indeed can be useful in practical settings. And with that, I would like to finish this talk by mentioning by referring just to the lady with the lamp that you probably have heard about her. So a long time ago, this nurse coming from England was able to use data, to extract data in order to combine her knowledge from being a nurse and also different visualization and statistics to make some significant changes in terms of a hospital where they had soldiers that were dying with a rate that was not necessarily described and was not necessarily what the doctors were expecting to see. So she managed to use statistics, she managed to use visualizations, she managed to collaborate with different partners there in order to take data-driven decisions and understand what's the phenomena. So she managed to do it 200 years ago. Nowadays, we have much more resources, we have much more knowledge, we have much more data. So I think it's a good opportunity to push this type of direction in terms of designing methods and techniques that are inspired by medical applications. So thank you for your attention, and here are some of the works that I discussed during the talk.